Namaskar. Welcome to the channel Anka Ananda Aharan, that is extraction of happiness from the teaching learning process of mathematics. Here, the purpose of this video is to enable the viewer to solve the problems of applied linear algebra from Gilbert-Strang book. Today we will discuss about matrix notation and matrix multiplications. Matrix addition is compatible if and only if matrix A and matrix B both have same number of rows and same number of columns. If C is equal to A plus B, then Cij, the ith row jth column element of capital C, is nothing but sum of the ith row jth column of element of A and ith row jth column element of B. For example, A is equal to 1, 2, 5, 7. B is equal to 2, 3, 4, 16. What will be A plus B? 1 plus 2, that means 3. And 2 plus 3, that is 5. 5 plus 4, that is 9. 7 plus 16, that is 23. Next, another operation that is defined on matrix is matrix multiplication. Two matrices A and B multiplication, that is A cross B, is compatible if and only if the number of columns of A equal to the number of rows of B, that is number of columns of first matrix is equal to number of rows of second matrix. If A is a m row n column matrix and B is a n row p column matrix, then A cross B is possible, and in this case it has m rows p columns and its general ith row jth column element of the resultant matrix can be obtained using this formula. That is, what we will do, the ith row of a first matrix is made dot product with the jth column of a second matrix. For example, suppose I want to get here this element. So what is its position? Its position is 2, 1. That means from the first matrix, I will select the second row. And from the second matrix, I will select the first column. I will make the dot products. That is 5 into 2, that is 10, plus 7 into 4, that is 28. So, which is my 38. So, in this way, matrix multiplication can be done. There are several other operations of matrices that we will discuss right now here. Some of the operations are scalar multiplication of a matrix. Suppose I have a matrix 2, 3, 5, 4 into C. It is nothing but 2C, 3C, 5C and 4C. That means each 4C. That means each element is multiplied with that C. It is called scalar multiplication property. Then another matrix operation, that is A transpose. How to get it? The rows of A will be converted as columns of it. That means suppose I have A is equal to 2, 3, 5, 4. Then what is A transpose? It will be 2, 3, 5, 4. So how I wrote? First row of A I have written as first column of A. Second row of A I have written as second column of A transpose. So here we got the A transpose from A, and if A transpose is equal to A, in this case which is not true, then A is a symmetric matrix. So there are some properties of transpose. What are the properties? Property 1, A transpose is equal to A. Property 2, some scalar times A whole transpose is equal to that scalar times A transpose. Then another property, A plus B whole transpose is equal to A transpose plus B transpose. Then another property, here there is a small change. AB means product of matrix A and B whole transpose is equal to B transpose A transpose. Here order is changed. Please observe. A is first written, B is second written, but in the transpose case, B transpose is first written, then A is written there. So then we have another set of definitions and some properties we will discuss now. These are the properties of transpose. If any matrix A has its transpose same, then this matrix A is said to be symmetric. A is symmetric. A is a symmetric matrix. And if A transpose is equal to negative of A, then A is a skew symmetric matrix. A is skew symmetric. SKEW. Skew symmetric. In this case, let us write down an example. Here, what will happen? Orbitally selected diagonal element 5, 8. And transpose position, that is here it is 1, 2 person, it is 2, 1 person. They should have same element. Suppose 6, 6. It is a 2 cross 2 symmetric matrix. Similarly, 5, 3, 11. Now it is 1, it is 1. It is 4, it is 4. Observe 1, 2 person, 2, 1 person, 1, 3 person, 3, 1 position. And here this is 2, 3 person, 6, 3, 2 person, 6. So these are two examples. Likewise, we can write several examples. Here there is no restriction on the diagonal elements. But all the transpose position elements must be same. But in case of skew symmetric matrix, here it is written as Aij, general position element, particular ith row jth column element is same as Aj in case of symmetric matrix. But in case of skew symmetric matrix, it is Aij is equal to negative of Aj. Transpose position contains negative element. So here diagonal element, if I is equal to j, I am writing, then what I will get? Aii is equal to minus of Aii. That means the diagonal elements are 0. So here a skew symmetric matrix, how to write down? All the diagonal elements must be 0. Suppose here I have written 3, then I should write here minus 3. Suppose here I wrote 6, here I should write minus 6. Suppose I wrote here 7, it should be minus 7. So this is a skew symmetric matrix. Another property for skew symmetric matrix is, and symmetric matrix, that is, for any square matrix, what is the, for any square matrix A, I can write A is equal to B plus C, where B is a symmetric matrix and C is a skew symmetric matrix. Every square matrix A can be written as a sum of two matrices where B is symmetric and C is skew symmetric. So here the formula for B is A plus A transpose by 2, and C, the formula for C is A minus A transpose by 2. Okay. So with this, some of the aspects of matrix notations and matrix multiplication we have discussed. Now let us go to the contents that are given in our Gilbertram book. How to get elementary row operations? We know that there are three types of elementary row operations. The first one is Ri plus Krj stored in Ri. About this elementary row operations, already 2 videos are being done and the link is already shared. So please go through them, then we can understand this video properly. So here it means kth multiple of jth row is added with ith row, and Ri interchange with Rj means interchange of ith row with jth row. Cri stored in Ri, that means ith row is replaced by its C times multiple. Now this is identity matrix. Here any operation after one elementary row operation, one elementary operation, whatever new matrix I am getting, that is called elementary matrix. So here observe here, that is after this operation what I am getting here, what it is 2 and it is 1, it is 2, it is 1. So there will be a change in 2 1 position and it should be replaced by this coefficient minus 3. So I got my elementary matrix, and its inverse is this minus sign will be replaced by plus sign. If it's a sign were plus, then I should have written here minus. Okay, then another row operation is row interchange. So if I am doing row interchange between 1 and 2, what I am getting? I am getting the first row. Observe what we have done, R2 interchange with R1. So what we got? The first position, first row is interchanged with second row of identity matrix, which is my F. So in this case, its inverse is also same. That means after committing the same interchange operation, that is if I will interchange first row with second row, again I will get my identity matrix back. Now the third operation, 5R2 stored in R2. That means this diagonal element is replaced 2 position diagonal element is replaced by 5. That means second row is multiplied with 5. Now its inverse is, multiplication's inverse is division. So that means the second row will be divided by 5. So its G inverse is this one. In place of 5, it is 1 by 5. So all these things are detailedly discussed in the videos made earlier. Now what are the effects of this elementary row operations or elementary matrices? If any elementary matrix is multiplied from left side of a given matrix, then row operation takes place, and if it is multiplied from right hand side, then column operation takes place. So here what happens? This is A is given as 1, 2, 3, 4, 5, 6, 7, 8, 9. EA, what is E? E was R2 minus 3R1 stored in R2. So this is my matrix. So from here, thrice the row 1 I will subtract. So what I am getting? 4 minus 3, it is 1. Now 5 minus 6, it is minus 1. Now 6 minus 9, it is minus 3. So only second row will get changed. So this row will be replaced by this. Rest 2 rows will remain as it is. Now when I am multiplying F with A from left side, that means these 2 rows will be interchanged. So that means 4, 5, 6 will be the first row and 1, 2, 3 is the second row. Similarly, when G is multiplied with A from left hand side, what I am getting? Each row element of a second row is multiplied with 5. So 4, 5, 6 of the second row is replaced by 20, 25, 30. So these are the some of the concepts that already we have discussed, but it is a just quick revision about elementary row operations. Next is we will discuss to the corresponding exercise problems of 1.4. Give 3 by 3 examples, not just geometrics of diagonal matrix. So it is diagonal matrix means it is a square matrix where all the non-diagonal elements are 0. This much. Diagonal elements can be 0, non-zero, no issue. So here 4 to 9. This is a diagonal matrix, and here it is a symmetric matrix. Already we have discussed how to write down a symmetric matrix, and it is an upper triangular matrix. Upper triangular matrix means a square matrix in which all the elements below the principal diagonal are 0. So what are the diagonal elements? The elements are said to be diagonal elements if their row position and column position are same. So here 1, 15, 9, they form the diagonal elements. Okay, so below it we have made 0. Then what is a skew symmetric matrix? A skew symmetric matrix means A transpose is equal to minus of A. That is, any element is transposed, its transpose position is negated. So here the diagonal elements will be 0. All the transpose position 1, 2 position is having 2, that means 2, 1 position will be minus 2. 1, 3 position is minus 3, that means 3, 1 position is 3. Here 2, 6, 2, 3 position is having 18, so 3, 2 position is minus 18. This is skew symmetric matrix example. Next, this is a rotation matrix, 2 cross 2 rotation matrix. Any vector multiplied to it will be rotated by an angle theta. So now A theta is equal to cos theta minus sin theta, cos theta. Using this definition and matrix multiplication property, we have to verify that A theta 1 A into A theta 2 gives me A of theta 1 plus theta 2. Then we have to obtain what is that A times theta, A theta times A minus theta. So here A theta 1 is this much, A theta 2 is this much. Their product gives us this value. Already these are plus 2 contents. Sine of cos of theta 1 plus theta 2. Cos of theta 1 plus theta 2. Similarly, sine of theta 1 plus theta 2. That formula we apply to get this verified. Next concept is what is A theta of A minus theta. So it is according to the previous property, it is A of 0, which is identity matrix. That means A theta and A minus theta are inverses of each other. Because any matrix, if I multiply A with B is equal to I, that is equal to B cross A, then I is an identity matrix. Compute the products. So here we know how to get the matrix multiplication. Here it is 3 row, 3 column, 3 column, 3 row, 1 column. So it is 3 row, 1 column. So how much it is? 4 into 3 plus 0 into 4 plus 1 into 5. That is 17, 4, 17. Here identity matrix with any vector is the vector itself. Here it is 2, 0, 1, 3 into 1, 1 is equal to 2, 4. So with this, we will conclude the video. In next video, we will discuss about some of the more aspects of applied linear algebra from Dilbostrom book. Thank you for your patient listening.